Alright, welcome back. So today we'll be considering one more example, and that example will be relevant to electronics engineering actually. Okay, so consider an electronic system that takes in a signal and outputs another signal. And this is actually consistent with how real systems work. Any electronic system, let's say for example a microphone, it takes in your voice, which essentially is a signal only, and it amplifies it. That's the output signal. Or consider this. Let's say you have a phone. It captures waves from the air or surrounding you, and it converts them into meaningful information. So that's what this is also. It's taking in a signal from the air, it's transforming it somehow, I don't know how, and it is converting it into another signal which is much more meaningful to us, like images or something else. Okay, so in this case I consider a very simple system, and that system is characterized by a function h of t. I'll explain what that is and how the signal x, that is the input signal x, is transformed is y of t is t of x. So actually I'll write it down a bit better. Oops, my bad. I'll write this down in a much more understandable way actually. This is t of x. So t of x is a function that corresponds to y, and t of x of t, that is the t of x at any instant t, is defined as an integral, and that integral is integral of x of tau times h of t minus tau d tau. Alright, so this integral, in short, I'll write it as x star h. So x star h is an operation that gives you another function. So this integral evaluates to x star h at the instant t, and this operation has a name which is a very popular operation in engineering. It's called convolution. So this thing is called a convolution operation, and this t is basically a transform. It's used to denote a transform actually from the set of all real functions to the set of all real functions. So what I'm doing is basically mapping one real function to another real function. That's what this is. And the technical term for such a thing is actually called a functional. So a functional is something that takes in a function and outputs another function. And in linear algebra parlance, this would actually be called a linear transform, but technical jargons aside, just know that this is a convolution operation. Simple as that. X star h means this integral. Alright, now the point of this video is going to be that if I have a pair of functions x and the transform of x, the transform being defined as the convolution. So if I have a set of these sort of things, then is this a vector space? Well, turns out it is, but how and why and what exactly are we getting out of this? So this is where I tell you a nice trick to prove anything complex as this. How do we prove it as a vector space or not? So in that case, we choose a bigger set, that is V. So the smaller set was just all functions x and transform of x. This won't cover all possible function tuples like fg, let's say, where f and g are both some real functions. Now consider the set of a tuple of real functions. Now if I define addition and multiplication as component wise, scalar multiplication, sorry, as component wise things, then obviously it's not that difficult to see how this thing can be a vector space over the field of real numbers. So the whole point of this is that I consider some bigger space, I establish that as a vector space, which is easy to do, and then using the three conditions for a subspace, I establish the required set, that is all pairs x and t of x, as a subspace of this bigger vector space V. So instead of just directly establishing this as a vector space, which might be a bit tedious or not that intuitive, consider this. Consider just establishing a bigger set like fg as a vector space, which is actually pretty easy. I mean, we have been looking at functions as vector spaces. We have been looking at an array of numbers as a vector space. Now this is just an array of functions. It's not exactly that difficult to show that this is actually a vector space, and it's actually pretty intuitive if you think about it, right? But this, on the other hand, it's a bit non-intuitive. It's not obvious at first glance. So what I'm going to do is prove that this set D is a subspace of this set V. Alright? Okay. And just for context, the identity in V is defined as 0 vector, that is a tuple of two 0 functions, and these functions are real, obviously. Okay. Now moving on to proving that D is going to be a subspace of V, consider the 0 element. So the 0 element is 0, 0. Now is this of the form, now the point is any element in D has to be of the form x t of x. Okay, the first component, transform version of the first component. That's how it should be. Now what is t of 0? T of 0 is integral of 0 times h of t minus t tau d tau, which obviously will be 0. It's not that difficult to see, because if you multiply anything with a 0 function, it will obviously result in another 0 function. And now anything that is 0 for any value that you give it, the integral of that will obviously be 0. Alright, so we have just shown that t of 0 is the same as 0, that is the 0 function, 0 here being the real function that is 0, not exactly the scalar value 0. Alright, and hence we have proven that the 0 vector from the original bigger vector space V is also contained in the set D. Okay, now define x1 and x2, x1 bar and x2 bar, which take the form x1 t of x1 and x2 t of x2. So these are valid elements from the set D. Alright, now look at x1 plus x2. Does it belong to your set D as well? Now x1 plus x2, I have defined it as component wise addition, but is this thing of the form x t of x, where x and t of x are both real functions? Is it of that form? Let's find out. For that, I'll consider the second component as the LHS, t of x1 plus t of x2. Now that is equal to x1 convoluted with h and x2 convoluted with h as well. I'll expand that into the integrals. Now the integral has the same limit over the same independent variable, and hence you can club this in actually. So now that I have clubbed this in, that is x1 multiplied by h of t minus t plus same with h2, same with x2 actually. And now I'll use the distributive property to club the two functions, that is x1 and x2 in, and multiply that with h of t minus t. Now notice that this thing over here is the same as x1 plus x2 convoluted with h, right? I mean, just think about it. So this is x1 plus x2 of tau times h of t minus tau d tau. Obviously that will be x1 plus x2 convoluted with h. That's the definition of convolution. And so this evaluates to be the t of x1 plus x2. And hence we have just proved that the addition of two vectors from D will also be a vector from D. So this thing will also belong to D, because t of x1 plus t of x2, we have just shown that it is t of x1 plus x2. Right? Okay. What about scalar multiplication now? If I multiply a tuple from D with any scalar a from R, so that will evaluate to be a times f and a times t of f. Now is this of the form t of a times f? Because it has to be, otherwise this thing won't belong to the subset D. So a times t of f can be expanded into this. Now we can take the scalar a inside the integral. That way it will be a times f of t, which can be written as a times f of t. Alright, this is how functions work. I'm just being a bit precise and rigorous over here. And so this by definition will actually be a times f convoluted with h, which is technically the transform of a times f. And so we have just proved that a times f comma t of a times f is also a member of D, and hence D is closed under scalar multiplication. We have also proved that D is closed under addition, and since there is also an identity element which was a bit too trivial to prove, with that we have satisfied the three conditions for D to be a subspace of V. Okay, so this is the whole linear algebra part. This is where the significance of that thing comes in. Now systems like this have a pretty nice name. Alright, so any system which transforms one signal to another signal like this using a convolution, so this type of thing is actually called a linear time invariant system. So people who want to know what this is, you can search it up on Wikipedia or any textbook about signals and systems. Actually, this is a very common term in engineering. It's called a linear time invariant system. So it is actually a very special type of system. Why? Because if we have any two inputs, x1 and x2, which are real functions by the way, if we have any two input signals, x1 and x2, with known outputs, we know what their output is going to be, and the output is going to be y1 and y2, which is again some other real signal. If we know this, then we also know the output of any linear combination of these two inputs. So a times x1 plus b times x2. The output for any linear combination of two inputs whose outputs are known is going to be the same linear combination of the outputs. That's the speciality of a linear system, a linear time invariant system. And in fact, over here, this thing right over here is actually the definition of linear system in engineering. If any system with two known input output pairs can actually work like this, where you take the linear combination of the input and you get the same linear combination of the known outputs, this over here is the definition of linear system in engineering. And what we just did right now, we just proved that the input output pairs form a vector space, and by the virtue of doing so, we have also proved that t of x1 plus x2, so x1 plus x2 is what? It's the, sorry, x1 and x2, let's say they are known inputs, so their outputs are known. So x1 plus x2 yields t of x1 plus t of x2, which is the same as t of x1 plus x2. So if I send x1 plus x2, I know that I'm going to get t of x1 plus x2. But instead of just going through the whole process or experiment and finding what exactly the transform of x1 plus x2 should be, I already know that that transform over here is the individual transform summed together. So that is t of x1 plus t of x2. These two things are already known. This is not known. But to find that, we can just add the known outputs. That's what this is. Similarly for scalar multiplication, I already know what the output of f is going to be. It's going to be t of f. But what's the output of a times f going to be? It's obviously going to be t of a times f, but can we somehow find that using what we already know? Obviously we can. It's a times t of f. We don't have to do separate experiments or separate simulations to find what is t of a times f again. We already know it's a times t of f, and t of f we already know. That's what this is. So the whole exercise of proving that the function pair x and t of x is a vector space where t is the convolution operation, the whole point was to actually put forth the significance of linear time invariant systems and linear systems in general actually. Alright, I hope you understand what this is about. I just bridged a gap between linear systems or linear time invariant systems and linear algebra. Both both have linear in them, but what exactly is the connection? So that's what this was about. Okay, so in the next video we'll look at another complicated example, and I'll try to simplify it down for you as much as possible. But this will be an example of what is not a vector space. So we have been looking at what is vector space, what is subspace, all these things, but next will be what is not a vector space. Okay, until then, stay tuned. Thank you.